Alright, the purpose of this video is to find the critical angle of a ray of light leaving water to air. Now, the critical angle is the angle of light that, when it comes in, makes the resulting angle equal to 90 degrees, like so. So this is going to require Snell's law, which is n sine of theta equals n sine of theta, or n2 sine of theta 2. With theta being your angle and the n being your indices of refraction. N is the first one is water leaving air, so the index of refraction of water is 133. And then N2 is air, and that index of refraction is 1. So we are going to plug this into Snell's law, in which 1.33 sine of the unknown angle, because that's theta 1, and we know theta 2 is 90 degrees, so 1 sine of 90. Now the sine of 90 equals 1, so the resulting thing after that is 133 sine of theta equals 1. And if 1.33 sine of theta equals 1, then sine of theta equals 1 over 1.33. And to get theta by itself, you take the inverse sine, and that equals, and if we put our calculator in degree mode, we get 48.75 degrees. Right, now that is how you find the critical angle using Snell's law. Our next problem is to determine the refracted angle of light entering a pool if the incident angle is 19 degrees. This is also Snell's law. Entering a pool now, so N1 is going to equal 1 because it's air, and N2 is going to equal 1.33. We are now flipped because we are going air to water.
And then 2 times 6 is 12.
Our first angle is, the incident angle is 19, so theta 1 equals 19 degrees, and theta 2 is unknown. So we're going to plug all this into Snell's law, and that is sine of 19 equals 1.33 sine of theta 2. We are solving for theta 2. So we then move it over to the other side, and sine of 19 degrees over 1.33 equals sine of theta, which if we discover that sine of theta equals, sine of theta equals 0.2447. Then to get theta by itself, again you take the inverse sine, and theta will end up giving you a final answer of 14.16 degrees. And that is your final refracted angle of a ray of light entering a pool. Thanks.